Hello to all dear students. In continuation with our chapter, that is design of dosage regimen, today we'll be talking about another topic, that is determination of dose and dosing intervals. So first of all, the success of drug therapy, it is highly dependent on the choice of drug, the drug product, and lastly the design of the dosage regimen, like how frequently you are giving the dose. That is also very much important in the success of any therapy. The choice of drug is generally made by the physician after careful patient diagnosis and physical assessment. Next, the choice of the product is like if we want a drug to produce an immediate action or a delayed action. That is also depend upon the patient. And lastly, the dosage regimen is based on the patient's individual characteristics and known pharmacokinetics of the drug. Ideally, the dosage regimen is designed to achieve the desired drug concentration at the receptor site to produce an optimal therapeutic response with minimum adverse effects. Individual variations in pharmacokinetics and pharmacodynamics makes the dosage regimens difficult. Therefore, the application of pharmacokinetics to the dosage regimen must be coordinated with proper clinical evaluation of the patient. Okay, so before actually starting into this topic, you need to know some basic concept, like here is a curve. On the x-axis there is time, and on the y-axis that is the plasma concentration. So basically this is the plasma concentration versus time curve. Suppose you give any drug via oral route and such kind of graph will be obtained. This point is known as the Cmax. Cmax means the maximum plasma concentration of the drug, and the time required to attain the maximum concentration of the drug is known as Tmax. Okay, Cmax is the maximum plasma concentration of the drug. Few more important thing is these two lines. The blue line is MEC, that is the minimal effective concentration, and this one is the maximum tolerable concentration. Minimal effective concentration means at this line, at this particular plasma concentration, the therapeutic activity of the drug will initiate, and the red mark that you can see, that is the maximum tolerable concentration. So any drug, if its Cmax is above the MTC, means it is likely to produce adverse effect. Okay, so here you can see, suppose there is a curve and the plasma concentration is below MEC, means it will fail to produce any kind of pharmacodynamic activity, means it will fail to produce any activation of receptor or enzyme or ion chains, means there won't be any action as such. And if a drug whose Cmax is above MTC, means it is likely to produce adverse effect. So we want a dose of a drug or a regimen, a dosage regimen, such that the Cmax is maintained in between these two lines. So the range, the plasma concentration range which is between MEC and MTC is known as the therapeutic range or therapeutic window. There are few drugs whose therapeutic window is very much small, whereas there are few drugs whose therapeutic window are wide enough. So what difference is there in the dosage regimen in such kind of drugs is that if the drug whose therapeutic window or therapeutic index is very much small, then what will happen? Suppose we are giving a dose of a larger dose for a longer dosage interval, okay, like this. So you can see the Cmax will be above MTC in this case. So any drug which is having a very narrow therapeutic window, in this case we need to give small doses at a regular interval, means instead of giving a like 1000 mg per day, we should give 20 mg 5 times a day, so that the Cmax is maintained in between this MEC and MTC line. Quite opposite, if a drug have got a wide therapeutic window, then in this case we can give a larger dose of the drug, because a larger dose may not exceed beyond the MTC line. One more important thing is this thing. This red line shows the steady state. In this steady state, this maximum concentration, this is known as the peak, and this one is known as the trough. And this peak and trough is very much important, and it particularly comes in the steady state concentration. Okay, so now we'll start the topic. Several methods may be used to design a dosage regimen. Generally, the initial dosage of the drug is estimated using average population pharmacokinetic parameters obtained from the literature and modified according to the patient's known diagnosis, pathophysiology, demographics, allergy, and any other known factor that might affect the patient's response to the dosage regimen. After initiation of the drug therapy, the patient is then monitored for the therapeutic response by clinical and physical assessment. After evaluation of the patient, adjustment of the dosage regimen may be needed. If necessary, measurement of plasma drug concentration may be used to obtain the patient's individual pharmacokinetic parameters from which the data are used to modify the dosage regimen, and further TDM in the patient may be needed. Various clinical pharmacokinetic software programs are available for dosage regimen calculations. The dosing strategies are based generally on pharmacokinetic calculation that were previously performed manually. Computer automation and pharmacokinetic software packages improve the accuracy of the calculation, make the calculations easier, and have an added advantage of maintaining proper documentation. However, the use of these software programs should not replace good clinical judgment. So this thing says that for initial dose we cannot set any dosage regimen. After giving an initial dosage of a drug to any person, after that we should check the pharmacokinetic parameter, and accordingly, by understanding its absorption, distribution, its elimination, half-life, the volume of distribution, after taking account of all these things, after this only we can set a dosage regimen. In addition, we have got various software by which we can do the calculation of dosage regimen, but these software programs should not replace the good clinical judgment that can be done manually. The package insert is a useful source for dose regimen. The section used in specific populations provides information that may apply to individual patients, such as special populations like pregnancy, labor and delivery, nursing mothers, pediatric use, geriatric use, hepatic impairment, renal impairment, and gender effects. Next, we'll talk about the individualized dosage regimen. When we are checking an individual person for setting a dosage regimen, we are not comparing a population, just an individual person. We are giving the drug and we are checking the pharmacokinetic and pharmacodynamic parameters, and then we are setting the dosage regimen. This is known as the individualized dosage regimens. The most accurate approach of dosage regimen design is to calculate the dose based on pharmacokinetics of the drug in the individual patient. This approach is not feasible for calculation of the initial dose. Obviously, after initial dose only we can calculate the thing. However, once the patient has been medicated, the readjustment of the dose may be calculated using pharmacokinetic parameters derived from measurement of the serum drug levels from the patient after the initial dose. Most dosing programs record the patient's age and weight and calculate the individual dose based on creatinine clearance and lean body weight. Next, dosage regimen based on population average. To some group of population, we will be giving a drug, and depending upon the average pharmacokinetic parameter, we can fix a dosage regimen. That is known as the dosage regimens based on population averages. This method, most often used to calculate a dosage regimen, is based on average pharmacokinetic parameters obtained from clinical studies published in the drug literature. This method may be based on the fixed or an adaptive model. So we have got two models in this. First one is fixed and another one is adaptive. We'll see what these things are. Fixed model assumes that population average pharmacokinetic parameters may be used directly to calculate a dosage regimen for the patient without any alteration. Usually, pharmacokinetic parameters such as absorption rate constant, bioavailability factor, apparent volume of distribution, and elimination rate constant are assumed to remain constant. Most often, the drug is assumed to follow the pharmacokinetics of a one compartment model. When a multiple dose regimen is designed, the multiple dosage equation based on principle of superposition are used to evaluate the dose. The practitioner may use the usual dosage suggested by the literature and then make a small adjustment of the dosage based on patient's weight and or age. So in fixed model, the dosage regimen is fixed. We are not adjusting it depending upon the individual patient. So that is fixed model. Whereas the adaptive model for the dosage regimen calculation uses patient variables such as weight, age, sex, body surface area, and known patient pathophysiology such as renal disease, as well as the known population average pharmacokinetic parameters of the drug. In this case, calculation of the dosage regimen takes into consideration any changing pathophysiology of the patient and attempts to adopt or modify the dosage regimen according to the needs of the patient. So as the name suggests, it is an adaptive model. So depending upon the patient's pathophysiological condition, whether it is he suffering from any kind of metabolic disorders or any organ disorder, depending upon the size of the patient, like its body surface area, his weight, his age, his gender, depending upon that we are doing the dosage regimen. But in fixed model, we are not checking the patient's individual concern. We are just giving a fixed dosage regimen depending upon the population average pharmacokinetic parameter. In the fixed model, the regimen is fixed, but in adaptive model we may adopt depending upon the patient variable parameters. In some cases, the pharmacogenetic data may be helpful in determining dosing. For example, clopidogrel has a black box warning cautioning use in patients who have slow CYP2D6 metabolism and who will therefore have slower activation of the prodrug to the active metabolite. Okay, so it is an example. Clopidogrel, it is a drug that has got a black box warning caution. Black box warning caution means there is a warning that an adverse effect may be any injury or it may also cause death. That is black box warning caution for the patient with slow CYP2D6 metabolism. So in the patient population who have got this problem of slow CYP2D6 metabolism, in these individual there is a warning of black box warning caution for consuming clopidogrel. So this thing we can get by a population average examination. However, an appropriate dose regimen has not been established for these patients. The adaptive model generally assumes that pharmacokinetic parameters such as clearance do not change from one dose to the next. However, some adaptive models allow for continuous adaptive change with time in order to simulate more closely the changing process of drug disposition in the patients, especially during a diseased state. Next is dosage regimen based on partial pharmacokinetic parameters. Means here the literature is not well established in this case. For many drugs, the entire pharmacokinetic profile of a drug is unknown or unavailable. Therefore, the pharmacokineticist needs to make some assumptions in order to calculate the dosage regimen in the absence of pharmacokinetic data in animals or humans. For example, a common assumption is to let the bioavailability factor F equal to 1 or 100%. Thus, if the drug is less than fully absorbed systemically, the patient will be under-medicated rather than over-medicated. This is a very simple example. Some of these assumptions will depend on the safety, efficacy and therapeutic range of the drug. So, these are the three ways by which dosage regimen can be adjusted. Next, we'll talk about determination of dose. How to determine a dose? What is a dose? Dose is the amount of drug which is given at a particular time so that some kind of therapeutic effect has to be produced. So, dose is nothing but it is the quantity of the drug that has to be administered to a patient at one time. So, that is a dose. So, the calculation of the starting dose of a drug and dosing interval is based on the objective of delivering a desirable therapeutic level of the drug in the body. Okay, so what is the desire? Do we want an immediate action or an extended action? For many drugs, the desirable therapeutic drug levels and the pharmacokinetic parameters are available in the literature. However, the literature in some cases may not yield complete drug information, or some of the information available may be equivocal. Therefore, the pharmacokineticist must make certain necessary assumptions in accordance with the best pharmacokinetic information available. For a drug that is given in multiple doses for an extended period of time, the dosage regimen is usually calculated to maintain the average steady state blood level within the therapeutic range. The dose can be calculated with the equation like the desired average concentration is equals to 1.44 into D naught is dose, into T half into F. F is the bioavailability divided by Vd into tau. Vd, you know, that is volume of distribution, and tau is the time duration. Now we'll have a practice problem. Suppose a pharmacokinetic data for clindamycin were reported by Dehaene et al. As follows. K, that is elimination rate constant, is equals to 0.247 per hour. The half-life is 2.81 h, that is hour, and volume of distribution is equals to 43.9 liters per 1.73 cubic meter. And what we need to calculate? We need to calculate what is the steady state concentration of the drug after 150 mg of the drug is given orally every 6 hours for a week. Assume the drug is 100% absorbed. Okay. So what all things are we have? We have some known parameters like elimination rate constant is given, the value of half-life is given, volume of distribution is given, even dose is given, that is 150 mg, and the duration, the time frequency, that is 6 hours for a week, it is given. Every 6 hours the drug has been consumed. So the solution, we can have the same formula, that is the desired average concentration is equals to 1.44 into D naught into T half into F divided by Vd into tau. So we'll place all these things and we'll get the value 2.3 microgram per ml. So with the help of this formula, we can calculate the steady state concentration. Next, one more problem will solve. According to Regme et al., the elimination half-life of tobramycin was reported to be 2.15 hours and the volume of distribution was reported to be 33.5% of body weight. So what we need to calculate? What is the dose for an 80 kg individual if a steady state level of 2.5 microgram per ml is desired? Assume that the drug is given by intravenous bolus injection every 8 hours. So for solution, we'll have the same formula, and what we need to calculate over here, we need to calculate the dose. D naught we need to calculate. So we'll keep the values according to the formula and we need to calculate D naught. So we'll rewrite this thing and we'll get 173 mg. So the dose should be 173 mg after every 8 hours. Next, a second part of this problem, the manufacturer has suggested that in normal cases, tobramycin should be given at a rate of 1 mg per kg every 8 hours. With this dosage regimen, what would be the average steady state level? Okay, so we need to calculate the average steady state concentration, and here the value of D naught has been changed, that is 1 mg per kg. So rewriting this thing, we'll get the formula of the value 1.6 microgram per ml. So because the bactericidal concentration of an antibiotic varies with the organism involved in the infection, the prescribed dose may change. The average plasma drug concentration is used to indicate whether optimum drug levels have been reached. With certain antibiotics, the steady state peak and trough levels are sometimes used as therapeutic indicators. Okay. Next, we'll talk about effects of changing dose and dosing interval on the maximum steady state concentration, minimum steady state concentration, and the average steady state concentration. So, what is this maximum steady state concentration, minimum steady state concentration? There is nothing but the peaks and troughs. Okay. Maximum steady state concentration is the peak, minimum steady state concentration is the trough, and the concentration in between these peaks and trough will be your average steady state concentration. During intravenous infusion, the steady state concentration may be used to monitor the steady state serum concentration. The blood samples withdrawn just prior to the administration of the next dose represent the minimum steady state concentration. To obtain maximum steady state concentration, the blood sample must be withdrawn exactly at the time for peak absorption, or closely spaced blood samples must be taken and the plasma drug concentration graphed. Okay, so when we can check the value of minimum steady state concentration, suppose first dose is given. Before giving the second dose, whatever the plasma concentration of the drug is left by the first dose, that will give the value of the minimum steady state concentration. Okay. Next, in practice, an approximate time for maximum drug absorption is estimated and a blood sample is withdrawn. Because of differences in rates of drug absorption, maximum steady state concentration measured in this manner is only an approximate of the true maximum steady state concentration. The average steady state concentration is used most often in dosage calculation, obviously to avoid any kind of adverse effect when it is more than MTC, or no effect when the concentration is less than MEC. The advantage of using the average steady state concentration as an indicator for deciding therapeutic blood level is that average steady state concentration is determined on a set of points and generally fluctuates less than the Cmax and C minimum at the steady state concentration. Moreover, when the dosing interval is changed, the dose may be increased proportionally to keep the average steady state concentration a constant. This approach works well for some drugs. For example, if the drug diazepam is given 10 mg 3 times a day or 15 mg 2 times a day, the same average steady state concentration is obtained with the help of the formula. The average steady state concentration equals to SFD0 divided by KVD into tau. In fact, if the daily dose is same, the average steady state concentration should also be same as long as the clearance is linear. However, when monitoring serum drug concentration, the average steady state concentration cannot be measured directly but may be obtained from the AUC by T during a multiple dosage regimen, because AUC by T will always be constant. The dosing interval must be selected while considering the elimination half-life of the drug, otherwise the patient may suffer from the toxic effects of the high Cmax at steady state or subtherapeutic effects of a low Cmax at steady state, even if the average steady state concentration is kept constant. Okay. For example, using the same example of diazepam, the same average steady state concentration is achieved at 10 mg 3 times a day or 60 mg every other day. Obviously, the Cmax at steady state of the latter dose regimen would produce a steady state concentration which is maximum several times larger than that achieved with the 10 mg 3 times a day. Obviously, suppose here in this example it is said that diazepam we are giving in one day 3 times. Okay, 10 mg morning, then 10 mg afternoon, 10 mg at night. So in total in one day it will become 30 mg in one day. And or else we have got a second option. Suppose we give diazepam 60 mg of 2 days, means on Monday we give 60 mg, Tuesday no drug, on Wednesday 60 mg. That means the same, isn't it? If we are giving 3 times a day 10 mg, in 2 days also it will become 60 mg, or else 60 mg one time you give and you don't give for 2 days. That also means the same. But the average steady state concentration in these two cases will be same, but what will happen to the peaks? The peaks in case of giving 3 times a day 10 mg, the Cmax will be in the level of therapeutic window. But when you are giving 60 mg for 2 days, means 160 mg on Monday you give and next 60 mg on Wednesday you give, then on Monday itself the peaks will be so much high that it is likely to produce an adverse effect. So average steady state concentration will be same in both the cases, but the maximum steady state concentration will be very much high when you give 60 mg one time or 10 mg 3 times a day. Okay, in general, if a drug has a relatively wide therapeutic index and a relatively long elimination half-life, then flexibility exists in changing the dose or dosing intervals tau using the average steady state concentration as an indicator. Okay, so we can do this thing if a drug have got a wide therapeutic range, means the therapeutic window should be high enough so that higher dose may not go beyond the MTC concentration. When the drug has a narrow therapeutic range, then the maximum steady state concentration and minimum steady state concentration must be monitored to ensure safety and efficacy. Obviously, please remember those blue line and red line. Blue line is the minimal effective concentration and red line I have shown as maximum tolerable concentration. So any drug that is having a very narrow therapeutic window, we cannot give a higher dosing like 60 mg for 2 days. Next 60 mg for another 2 days. Like this we cannot give. In this case, any drug that have got a very narrow therapeutic range, this case we should follow 10 mg 3 times a day. But any drug that have got a wide therapeutic window, in this case we can give 60 mg for 2 days. Okay, because the Cmax will always be below the MTC value. As the dose or dosage interval change proportionally, the average steady state concentration may be same, but the steady state peak, that is maximum steady state concentration, and the trough, that is minimum steady state concentration, drug level will be changing. The maximum steady state concentration is influenced by the dose and dosage interval. An increase in the dose given at a longer dosage interval will cause an increase in the maximum steady state concentration and decrease in the minimum steady state concentration. That is obvious. In this case, the maximum steady state concentration may be very close or above the minimal toxic dose drug concentration. However, the minimal steady state concentration may be lower than the minimal effective drug concentration. In this latter case, the low minimal steady state concentration may be subtherapeutic and dangerous for the patient depending on the nature of the drug. Obviously, so we cannot say that any drug that is above the MTC value is dangerous and any drug that is below the minimal effective concentration will be safe, because there are few drugs. There are few patients who are alive just because of drugs, and if the plasma concentration of the drug is below the minimal effective concentration, means obviously that will be life threatening to those patients who are depending upon those drugs. The drug dose is often related to the frequency of the drug administration. The more frequently a drug is administered, the smaller the dose is needed to obtain the average steady state concentration. Thus, a dose of 250 mg every 3 hours can be changed to 500 mg every 6 hours without affecting the average steady state plasma concentration of the drug. So this statement says that if you are giving very frequently a dose, then better to reduce the dose, and if you are giving a dose at a longer interval of time, means we need to increase the dose of the drug. However, as the dosing intervals get longer, the dose required to maintain the average plasma drug concentration gets correspondingly larger. When an excessively long dosing interval is chosen, the larger dose may result in a peak plasma levels that are above the toxic drug concentration and trough plasma concentration that are below the minimal effective concentration, even though the average steady state concentration will remain the same. So even this statement says the same whatever I have shown in the first initiation of this video itself with the help of the graph. Okay, so a dose should be adjusted such that the peak should be below the maximum tolerable concentration and the trough should be above the minimal effective concentration. In general, the dosing interval for most drugs is determined by elimination half-life. Drugs such as penicillins, which have relatively low toxicity, may be given at intervals much longer than their elimination half-lives without any toxicity problems. Drugs having a narrow therapeutic range such as digoxin and phenytoin must be given relatively frequently to minimize the excessive peaks and trough fluctuation in the blood levels. Okay, again we'll take this an example. For example, the common maintenance schedule for digoxin is 0.25 mg per day and the elimination half-life of digoxin is 1.7 days. Okay, so digoxin per day, the dosing should be 0.25 mg in one day and the elimination half-life is 1.7 days. So you can see almost it requires 2 days for half of the drug to get eliminated out. In contrast, penicillin G is safer drug. Penicillin G is given at 250 mg every 6 hours, while the elimination half-life of penicillin G is 0.75 hours. Means not even 1 hour, just 45 minutes. Within 45 minutes, the half of the drug is getting eliminated for penicillin G. But for digoxin, it is taking almost 2 days. So you can see for digoxin, the state time of digoxin in our body is more. For penicillin G, the state time of penicillin G in our body is less. Penicillin is given at a dosage interval equal to 8 times its elimination half-life, whereas digoxin is given at a dosing interval only 0.59 times its elimination half-life. The toxic plasma concentration of penicillin G is over 100 times greater than its effective concentration, whereas digoxin has an effective concentration of 1 to 2 nanogram per ml and a toxicity level of 3 nanogram per ml. The toxic concentration of digoxin is only 1.5 times effective concentration. Therefore, a drug with a large therapeutic index can be given in large doses and at relatively long dosing interval. So what this example says? This example says that digoxin, the therapeutic dose of digoxin is 0.25 and you just increase the dosing, means more than just 1 to 2 times more than the therapeutic dose, and it will produce a toxic effect with digoxin. But with penicillin G, you increase the dose of penicillin G 100 times more than its therapeutic dose, then also it will not produce any kind of toxic effect. That means penicillin G have got a wide therapeutic window, but digoxin have got very narrow therapeutic window. So what might be the dosing of digoxin? It should be frequently a small dose, but for penicillin G you can give a larger dose for a longer dosage interval, because it will not produce any therapeutic adverse effect. Okay, means not adverse effect as such with penicillin G. Next, we'll talk about determination of both dose and dosage interval. For now, both the dose and dosing interval should be considered in the dosage regimen calculation. For intravenous multiple dosage regimen, the ratio of maximum steady state concentration by minimum steady state concentration may be expressed by, the equation is maximum steady state concentration divided by the minimum steady state concentration is equals to Cp0, means the initial plasma concentration, into 1 minus e to the power of minus k tau. K is the elimination rate constant, tau is the dosage interval, divided by the C naught P into e to the power of minus k tau into 1 minus e to the power of minus k tau. Now this equation can be simplified as the maximum steady state concentration divided by the minimum steady state concentration is equals to 1 divided by e to the power of minus k tau. From this equation, a maximum dosage interval may be calculated that will maintain the serum concentration between the desired minimum steady state concentration and maximum steady state concentration. After the dosage interval is calculated, then a dose may be calculated. So what this slide says, why we need to calculate a maximum dosage interval? Because a dosage interval should be given at a maximum dosage interval, because if you are giving a drug very much frequently means there will may be a problem of accumulation. If you are giving a dose at a very bigger time interval means the plasma concentration may fall below the minimal effective concentration. So we need to give a dose at a regular interval such that the plasma concentration should be in between the C minimum and C maximum for the steady state concentration. Now we'll have a practice problem. Suppose the elimination half-life of an antibiotic is 3 hours with an apparent volume of distribution equivalent to 20% of the body weight. The usual therapeutic range for this antibiotic is between 5 and 15 microgram per ml. Adverse toxicity for this drug is often observed at serum concentration greater than 20 microgram per ml. Calculate a dosage regimen, that is a multiple intravenous doses that will just maintain the serum drug concentration between 5 and 15 microgram per ml. So in this problem what we need to calculate? We need to calculate the dosage regimen, that is tau. Tau is the dosage regimen. What things are given? Elimination half-life of a drug is 3 hours. That is given, means 0.693 by 3 we should do, and we have got minimum steady state concentration, that is 5 microgram per ml, maximum steady state concentration, that is 15 microgram per ml. Okay, so many known values are given. Now we'll try to solve this with the help of the same formula, that is maximum steady state concentration divided by minimum steady state concentration is equals to 1 divided by e to the power of minus k tau. Now we'll write all the known values, like 15 is the maximum steady state concentration, 5 is the minimum steady state concentration, k, the value is k is given that elimination half-life is 3 hours, so 0.693 divided by 3, and tau. Tau we need to calculate, dosage regimen means dosage interval we need to calculate. So we'll rewrite this thing. Now take the natural log on both the side, and we'll have the value tau equals to 4.76 hour. So this is the dosage interval. At every 4.76 hour we need to give the dose. But what is the dose? We don't know the dose. So next we will calculate the dose, then determine the dose required to produce from the maximum steady state concentration from the first equation, and we'll substitute it in this manner. So we'll get the maximum steady state concentration is equals to d naught by Vd divided by 1 minus e to the power of minus k tau. Now add all the values, solve for dose d naught, letting Vd 20 mg per kg, means we in the problem itself it is given 20% of the body weight. So we'll have the value like this, and by calculating we will have the value of d naught, that is dose equals to 2 mg per kg. Okay, so after every 4.76 hours we need to give 2 mg per kg of dose for that individual. Next we will cross check the value. To check this dose for therapeutic effectiveness, we need to calculate that how much amount of minimum steady state concentration and maximum steady state concentration we are getting. Means with the help of this dose with the help of 2 mg per kg dose which is given after every 4.76 hour, are we getting the C minimum steady state concentration and maximum steady state concentration 5 and 15 mg per microgram per ml, we are getting it or not? We should cross check this thing with the help of the same formula. Rewrite this thing, and we'll have a C minimum, that is minimum steady state concentration of 4.99 microgram per ml. Okay, and what was the minimum steady state concentration given in the problem? That is 5 microgram per ml. So it is almost same. Similarly, we'll cross check with the help of the maximum steady state with the average steady state concentration. See, minimum steady state concentration is 5, maximum steady state concentration is 15. So what might be the average? It will be almost 10 or maybe 9.5 or 10.5, something like that. We will cross check this thing. So average steady state concentration is equals to d naught by Vd into k tau. So we'll put all the values and we'll get 9.09 microgram per ml, which is the average steady state concentration. Okay, so by solving this equation we got that by calculation the dose of this antibiotic should be 2 mg per kg every 4.76 hours to maintain the serum drug concentration between 5 and 15 microgram per ml. So this is the result. But in practice, rather than a dosage interval of 4.76 hours, the dosage regimen and the dosage interval should be made as convenient as possible for the patient, and the size of the dose should take into account the commercially available drug formulation. Therefore, the dosage regimen should be recalculated to have a convenient value that is below the maximum possible dosage interval, and the dose adjusted accordingly. Okay. Next, we'll talk about drug accumulation during multiple dosing. For calculation of multiple dose regimen, it is necessary to decide whether successive doses of drug will have any effect on the previous dose. We are giving first dose. We are giving second dose. Before giving second dose, what is the plasma concentration maintained by the previous dose? That we need to check. If we are continuously giving first dose, second dose, third dose, fourth dose, continuously we are giving, there are chances of accumulation. So the principle of superposition assumes that early doses of drug do not affect the pharmacokinetics of the subsequent doses. Therefore, the blood levels after the second, third or nth dose will overlie or superimpose the blood level attained after the n-1th dose. In addition, from this graph you can see the AUC for the first dose is equal to the steady state area between the doses. Okay, so area under curve, the absorption always remains the same, whether it is first dose or whether it is a dose given at the steady state. Okay, now the principle of superposition allows the pharmacokineticist to project the plasma drug concentration time curve of a drug after multiple consecutive doses based on the plasma drug concentration time curve obtained after the first dose. So the basic assumptions are that the drug is eliminated by first order kinetics. Secondly, that the pharmacokinetics of the drug after a single dose are not altered after multiple doses. We should assume these things, and this table is based on the same assumption. Like here you can see the columns. First column is the dose number, first dose, second dose, third dose. You can see the numbers 1, 2, 3, 4, 5, 6. 1 is the first dose, second dose, third dose, fourth dose, fifth dose and the sixth dose. Beside that, I have got another column of time. So you can see first dose is given at 0 hour, second dose is given at 4th hour, third dose is given at 8th hour, fourth dose is given at 12th hour. So what is the dosing interval? At every 4 hours we should give a dose. Now when we check the first dose, at the 0 hour the plasma concentration of the drug will be obviously 0 microgram per ml, and after 1 hour it will be 21 microgram per ml. At second hour it will be still more, and at the third hour you can see the dose will be maximum, that is 19.8 microgram per ml. And after that, the fourth hour the dose will be start reducing up to 24 hours. You can see the first dose what you have given at 0 hour, it was 0, and the peak level of that dose was at the third hour. Okay, so at every third hour the Cmax will be attained. Okay, so Tmax is the third hour, and the first dose will be still remaining in our body up to the 24 hours also. Okay, that is 0.53 microgram per ml. It is still remaining. Now after 4th hour the second dose is given. Okay, a second dose is given, and at the 4th hour obviously it will be 0. Now we know at every third hour the dose will be at the Cmax. So for second dose it will be at the 7th hour. So you can see at the 7th hour it will be the maximum, that is 19.8, but at the 7th hour little bit amount of the first dose will also be remaining, that is 10.1, and in total you can see the amount of the drug remaining in our body at 7th hour will be 29.9 microgram per ml. See, this table is done on an assumption means first time a dose is given, okay, and on the basis of the first dose the value of second, third, fourth, fifth and sixth doses are being written. So you can see still the drug is not completely eliminated out of our body and a second dose is been given, okay, and you can see simultaneously a third dose of the drug is been given. So as you are increasing the dose, the accumulation of the dose is getting increased inside our body, okay. Next, on the 11th hour the third dose will be at the maximum, but with the third dose, the second dose we have 10.1, the first dose 5.06. so in total at the 11th hour it will be 35 microgram per ml, means this much amount of drug is getting accumulated in our body at the 11th hour. Now the plasma drug concentration after multiple doses may be predicted from the plasma drug concentrations obtained after a single dose, okay. At single dose only we have done all those plasma concentration, and same we have repeated for second dose, third dose and so on and so forth. In the table the plasma drug concentration from 0 to 24 hours are measured after a single dose. A constant dose of drug is given after every 4 hours, and the plasma drug concentration after each dose are generated using the data after the first dose. Thus, the predicted plasma drug concentration in the patient is the total drug concentration obtained by adding the residual drug concentration obtained after each previous dose. Okay, so these all statements says the same. The superposition principle may be used to predict the drug concentration after multiple doses of many drugs. Because the superposition principle is an overlay method, it may be used to predict drug concentrations after multiple doses given at either equal or unequal dosage interval. For example, the plasma drug concentration may be predicted after a drug dose is given every 8 hours or 3 times a day before meals at 8 am, 12 noon and 6 pm. There are situations, however, in which the superposition principle does not apply. In these cases, the pharmacokinetics of the drug change after multiple dosing due to various factors, including changing pathophysiology in the patient, saturation of a drug carrier system, enzyme induction and enzyme inhibition. Even the drugs that follow non-linear pharmacokinetics generally do not have predictable plasma drug concentrations after multiple doses using the superposition principle. So in this case, it will not apply. If the drug is administered at a fixed dose and a fixed dosage interval, as is the case with many multiple dose regimen, the amount of drug in the body will increase and then plateau to a mean plasma level higher than the peak plasma concentration obtained from the initial dose. When the second dose is given after a time interval shorter than the time required to completely eliminate the previous dose, the drug accumulation will occur in the body, obviously. In other words, the plasma concentration following the second dose will be higher than corresponding plasma concentration immediately following the first dose. However, if the second dose is given after a time interval longer than the time required to eliminate the previous dose, drug will not accumulate. Now by this graph you can see amount of drug in body versus time graph is there. Amount of drug in the body as a function of time. Equal doses of drug were given every 6 hours upper curve and 8 hours lower curve. The absorption rate constant and the elimination rate constant remains the constant. So because of which a steady state concentration is being maintained. So you can see when a drug is given after every 8 hours, the amount of drug in the body will be more. As compared to the drug given every 8 hourly, the amount of drug in the body will be a bit lesser. Next, as repetitive equal doses are given at a constant frequency, the plasma level time curve plateaus and the steady state is obtained. At steady state, The plasma drug level fluctuate between the maximum steady state concentration and minimum steady state concentration. Means still steady state has not been attained. It is about to attain the steady state. And once the steady state is obtained, the maximum steady state concentration and minimum steady state concentration are constant and remain unchanged from dose to dose. In addition, the area under curve is constant during the dosing interval, as you can see in this graph. The AUC for first dose, or you can see the AUC for when after attaining the steady state concentration. Both are same. The maximum steady state concentration is important in determining the drug safety. Obviously, the maximum steady state concentration should always remain below the maximum tolerable concentration. The maximum steady state concentration is also a good indicator of drug accumulation. So, two importance of determining this maximum steady state concentration. First one, it is required for maintaining the safety, or else adverse effect may produce, and secondly, it is also useful for determining the drug accumulation. If a drug produces the same maximum steady state concentration at steady state compared with the Cn-1 max after a first dose, then there is no drug accumulation. Cn-1 max is any maximum concentration of the drug after the first dose. If the maximum steady state concentration is much larger than the Cn-1 max, then there is significant accumulation during the multiple dose regimen. Accumulation is affected by the elimination half-life of the drug and the dosing intervals. The index for measuring the drug accumulation is R. R is equals to the maximum steady state concentration divided by Cn-1 max. Okay, maximum steady state concentration means it is the peak at the steady state concentration, and Cn max is any maximum concentration, any peak just before or after steady state, but after the first dose. So suppose this is the first equation. Now substituting the C max after the first dose and at steady state, we'll have a formula somewhat like this, and we will give it as equation number 2, and we can rearrange it in this manner. R, that is accumulation, is equals to 1 by 1 minus e to the power of k tau. Equation 2 shows that drug accumulation measures with R index depends on the elimination constant and the dosing interval and is independent of dose. So this means accumulation mainly depends upon two important things. First of all, how much is the dosage interval. Second thing is how much amount, means how is the elimination. Is the drug eliminating or not, and what is the interval, how much is the input and how much is the output. Obviously, dosing interval is the input, how frequently you are giving the dosing, because of which the accumulation may get affected. Even how much is the output, how much amount of drug is getting eliminated, on this factor also relies the accumulation. It does not depend upon the dose, because if dose is more, obviously elimination will also be more, but if dosing interval is more, it will affect the accumulation. For a drug given in repetitive oral doses, the time required to reach steady state is dependent on the elimination half-life of the drug and is independent on the dose size, the length of the dosing interval and the number of doses. Lastly, for example, if the dose or dosage interval of the drug is altered as shown in this figure, the time required for the drug to reach steady state is same, but the final steady state plasma level changes proportionately. Next, we'll talk about loading dose and maintenance dose. Since extravascular doses require time for absorption into the plasma to occur, therapeutic effects are delayed until sufficient plasma concentration are achieved. Like there are few drugs which will require more time to attain a steady state. Means slowly it will achieve the steady state, means half-life is really very bigger, so that steady state attainment of steady state will be taking a much longer time. So to reduce the onset time of the drug, that is the time it takes to achieve the minimal effective concentration, a loading dose or a priming or initial dose of drug is given. The main objective of the loading dose is to achieve desired plasma concentration as quickly as possible. If the drug follows one compartment pharmacokinetics, then in theory, steady state is also achieved immediately following the loading dose. Thereafter, a maintenance dose is given to maintain this every steady state concentration and the steady state so that the therapeutic effect is also maintained. In practice, a loading dose may be given as a bolus dose or a short-term loading dose after intravenous infusion. As discussed earlier, the time required for drug to accumulate to a steady state plasma level is dependent mainly upon its elimination half-life. So the time needed to reach 90% of the average steady state concentration is approximately 3.3 half-life, and the time required to achieve 99% of the average steady state concentration is equal to approximately 6.6 half-lives. For a drug with a half-life of 4 hours, it will take 13 hours for 90% of the average steady-state concentration and 26 hours for attaining 99% of the average steady-state concentration. For drugs absorbed rapidly in relation to time, for a drug absorbed rapidly in relation to its elimination, means the absorption rate constant is very much high as compared to the elimination rate constant, and that are distributed rapidly. The loading dose DL can be calculated by the following formula. DL by D naught is equals to 1 divided by 1 minus e to the power of Ka tau into 1 minus e to the power of K tau. Okay, so it is a case where the absorption rate is very much high as compared to the elimination rate. For extremely rapid absorption, as when the absorption of Ka tau is larger, or in case of intravenous infusion, e to the power of minus Ka tau becomes approximately 0, and therefore this equation can be reduced as dl by d naught is equals to 1 by 1 minus e to the power of K tau, because absorption is very much faster. Here dl is the loading dose and d naught is the normal dose. The loading dose should approximate the amount of drug contained in the body at the steady state. So the dose ratio, we have got a dose ratio is equal to loading dose divided by the maintenance dose. As a general rule of thumb, if the selected dosage interval is equal to the drug's elimination half-life, then the dose ratio calculated from the above equation is equals to 2. In other words, the loading dose will equal to the double the initial dose. This figure shows the plasma level time curve for dosage regimen with equal maintenance doses but different loading doses. Okay, so dose ratio means loading dose divided by the maintenance dose. Loading dose means initial dose, the first dose. Maintenance dose means whatever we are giving dose at a regular interval. If that is equals to 2, that is a favorable dose, you can see. Now in the graph you can see few curves are given, curve A, B, C and D. You can see in curve B, DL by DM, the loading dose by maintenance dose is equals to 2, and this is the what desirable dose we want. When it is equals to 2, then what we can see, the B, the initial dose is obviously above the minimal effective concentration. But when we see the curve A, DL by DM is equals to 3, where loading dose is extremely high, that at a single dose a maximum, it means if a drug that have got a narrow therapeutic window means it may go beyond the MTC value, whereas the curve C, it is just above the MEC value, whereas the curve D is below the MEC value. So DL by DM should never be equals to 1. Next, a rapid approximation of loading dose DL may be estimated from the formula DL equals to VD into C average divided by S into F, where the C average infinity is the desired plasma drug concentration, S is the salt form of the drug, and F is the fraction of the drug bioavailability. This above equation assumes very rapid drug absorption from the immediate release dosage form. The DL that is the loading dose calculated by this method has been used in the clinical situation for which only an approximate of the loading dose is needed. So this is the equation by which we can calculate the loading dose. Next we'll talk about a maintenance dose. A maintenance dose is the maintenance rate, that is mg per hour, of the drug administered equal to the rate of elimination at steady state. It is also defined as the amount of drug required to keep a desired mean steady state concentration in the tissue. It is administered after loading dose, and calculation of this thing is done by DM, that is maintenance dose, is equals to Cp into Cl divided by F. Cp is the plasma concentration, Cl is the clearance, and F is the bioavailability. And this is how we can calculate the maintenance dose. And by this we'll have complete our topic. I hope you will